Right, these are the skills that you should have done from the previous lesson, C 8.1. If you're not sure on any of these things, then do go back over this lesson. So first up was how to actually measure the rate of reaction. You either do that by doing the quantity of reactant used divided by the time, or the product formed divided by the time. Basically, you just got to remember to always divide by time. In terms of how you're going to measure that quantity, you could do a mass or a volume, depending on what the reaction is. And of course, the units will depend on what that quantity is. The mean rate is literally where you just take a volume of gas, like, I don't know, 20 centimeters cubed produced in 10 seconds. You do 20 divided by 10. All right, so that obviously gives you a mean rate of reaction. To get the exact rate of reaction from a curve, first of all, you might have to draw the curves. Obviously, I haven't seen you doing that, but you can do that yourselves. And then if you have got a curve, obviously you need to draw a tangent, just like I showed you last time. Gradient of that tangent should be calculated just like in the last lesson. So that's the stuff that we did last time. Right, today these are the things that we're going to look at. I'm not particularly going to talk through these. However, this time I am going to go through them again at the end just to make sure that we're happy with those. Right, so this first slide, it says demo. This is a demo I normally do in the classroom to introduce this particular topic, so collision theory. There is a little YouTube clip down there. It's highly exciting. Do have a look at it. We'll just use this to have a look at some of the chemicals that you should know. So hopefully you might recognise that first one, and you should definitely recognise the second one. So have a go at writing those down underneath. Hopefully you wrote ammonia and hydrochloric acid. Interestingly, technically, I should have written hydrogen chloride there because acids, by definition, only show their acidic nature when they are dissolved in water. So because the state symbol is a G, it should really say hydrogen chloride. But I suspect you all wrote hydrochloric acid. When those two things react, it's just a simple acid base, and they add together, and you get that stuff, which you should recognise as ammonium chloride. In terms of why we're looking at that, if you look at the demo underneath, because ammonia gas and hydrogen chloride gas are both colourless, if you put them at each end of the tube, they slowly diffuse down the tube, and where the particles collide, you will get a white solid of ammonium chloride. So the first part of this lesson is looking at something called collision theory and something called activation energy. You might remember the activation energy from the topic C7. Right, first up, a couple of simple definitions as to what they are. Right, hopefully you know that for a chemical reaction to occur, obviously you've got to have particles colliding or crashing into each other, and there's got to be enough energy to break the bonds, otherwise they'll just bounce off essentially. This idea is known as collision theory. That's how it will be referred to in the exam. And the minimum energy required for a successful collision being one where you break the bonds, is known as the activation energy. And you might remember on our reaction profile graphs, we labelled the activation energy as being the energy from the products to the peak of those curves, which is where all of the bonds have been broken. Right, this slide just gives you a visual representation of a of activation energy, I guess. So if you look at the reaction between nitrogen monoxide and ozone, essentially what they're saying here is if these two gases just collide, then there is one possibility. Possibility number one is that they collide and the energy is not enough to break either the O bonds or the NO bonds, and you literally just end up with the same thing. That would be an ineffective or an unsuccessful collision. Obviously, possibility number two is that there is enough energy here to break those bonds, and then those nitrogen oxygen atoms can recombine and form the products, which in this case are NO2 or O2, and that is an effective or successful collision. Okay, so we're now going to look at how you can increase the rate of reaction. And of course, if you want to increase the rate, that essentially means increasing the number of successful collisions. Right, how can we do this? So last lesson, I asked you to think about this and see if you can remember the different ways to actually increase the rate of reaction. So in no particular order, you should have had the following. Number one, increase the temperature. Obviously, if you increase the temperature, the particles will be moving faster, so therefore there will be more collisions and therefore more successful collisions. Also, they will be moving they have greater energy, so each of those collisions will clearly have a greater energy, so therefore there will be more successful collisions. If you have a solution, you can increase the concentration. What that really means is increase the number of particles per unit volume. Essentially, that then means increase the number of collisions and therefore successful collisions. Similarly, for a gas, if you increase the pressure, that again will give you more particles per unit volume, which will therefore again increase the number of collisions and therefore successful collisions. If you have a solid, you can increase the surface area, and we're going to look at that one in more detail in a second. And finally, of course, you can add a catalyst, which provides an alternative reaction pathway with a lower activation energy. So this part of the lesson, we're going to have a look at specifically surface area and how that affects reaction rate. First up, this only applies to solids. So that's probably pretty obvious, but that's something to remember. So I'm hoping you might know what you have to actually do to a solid to increase the surface area. Have a think about that. And hopefully you said to break it up or smash it up into small pieces or turn it into a powder or words to that effect. Right, so particularly the types of solids that have a very large surface area. Well, it was one of the ones I mentioned just now. And that, of course, would be powders. So if you have a powdered solid, then it will often have a very high reaction rate. This is why iron filings, when you put them in Bunsen burners, basically look like sparklers. Whereas if you put a solid lump of, I don't know, a nail in a Bunsen, doesn't really do very much. Okay, so see if you can go do some drawings. A solid with a large surface area and a solid with a small surface area. Give that a go. So you should have done something like this, but probably without all of the jazzy extra bits and pieces. So this, just for fun, is the reaction between magnesium and hydrogen ions. So if you like, magnesium and hydrochloric acid, which forms hydrogen gas, and magnesium chloride. We've removed the chloride ions because they are spectator ions. Right, however, that's not really what the point of this was. The point of this was that if you have a large lump, then obviously the hydrogen ions in this case, or any of the reactor molecules, can only collide with the outside. Yeah, all of these in the middle cannot react with the acid until these ones have reacted away. Whereas if you increase the surface area, break it up into a powder, you can see that all of these can get in here and you've got a much larger number of collisions that are going to occur between the reactants, and therefore the number of successful collisions increases, therefore the rate will increase. Right, on this slide we're going to have a little look at how the surface area and volume of a cube are related in the surface area to volume ratio. So what we've got here is 3 large cubes which have all got the same overall dimensions of 10 by 10 by 10. However, we've broken them up into smaller parts. So when it's talking about the cublet, it's talking about just one of these parts. So this one obviously has not been broken up, so it's just 10 by 10 by 10. This one has been broken up, so overall it's still the same. But each of the little ones, the cublets, is 5 by 5 by 5, and this one has been broken up even more, so each of these little cublets is 1 by 1 by 1. So the total volume is going to be the same for each one, and hopefully what we're going to look at is see what happens to the total surface area as you work through these. So have a go at filling these in. I'm assuming you know how to work out surface area and volume, and see what you come up with. Right, let's look at the second one. Right, so the final row, hopefully you've done that. So we have surface area is going to be 1 times 1 times 6. Volume, of course, is going to be 1 times 1 times 1. How many smaller cubes are there? Well, if you've done a little bit of counting, you would have spotted that there are 1,000. Right, so that's 10 across each one. So the total area, surface area, sorry, it's going to be 6,000, 6 times 1,000. Total volume, of course, is the same. So you now have your ratio of 6 to 1. So what does all this mean? Well, if you have a look at the surface area to volume ratio, you can see there is a clear pattern. As the side of a cube decreases by a factor of 10, so here's the side of the cube, decrease from the first one to the bottom one, so decrease by a factor of 10, the surface area to volume ratio increases by a factor of 10. So if you have a look, right, the volume has gone down by a factor of 10, so the surface area to volume ratio has increased by a factor of 10. So basically what that means is if you have very, very small pieces of solid, the surface area will be extremely large compared to the same volume of large pieces. So very common exam questions are asking you to state and explain how changing surface area or temperature or concentration will affect the rate of reaction. So see if you can complete this sentence. Increasing the surface area of a solid will speed up the reaction because. Just a little note, try and make sure you're using the correct language here. So we're going to be looking for the word particles, they're going to be looking for the word collisions. So you could have written something like this. There are more particles exposed to react. So if you increase the surface area, there are more particles exposed to react. Therefore, there are more successful collisions. Therefore, the rate of reaction increases. Okay, so finally, let's have a look at the spec statements, which were there at the beginning, that we're supposed to have covered, and see if you're okay with those. So first up, it says you're supposed to know about the factors which affect the rates of chemical reactions. And hopefully you are aware that concentration is one thing, pressure is another one, surface area is another one, temperature is another one, and catalyst is the final one. Then this thing called collision theory explains how these factors affect the rates. These chemical reactions only occur when the particles collide with enough energy, and the minimum energy that particles have to react is called the activation energy. And you are supposed to be able to predict and explain the effects of change in size of pieces of reacting solid in terms of surface area to volume ratio. One thing I will just say is just be a little bit careful with surface area because, of course, it's very, very easy. They're asking about sizes of pieces. A large piece of solid will have a small surface area. So just be careful from a language point of view on that one.